welcome everyone to this first technical session of our PBD4 event. It's going to be a great kickoff. We're starting off with our main event, the Ishihara Lecture. My name is Ross Boulanger. I'm at the University of California in Davis. My co-moderator is Dr. Lanmin Wang, is our conference chair. He has some duties to take care of and will join us shortly. So he's asked me to proceed with kicking this session off. But I'd start by noting that the Ishihara Lecture was established in 2004 by the Technical Committee on Geotechnical Earthquake Engineering, that's TC203, as part of the International Society of Soil Mechanics and Geotechnical Engineering. And the lecture pays homage to the significant scientific and professional achievements of Professor Kenji Ishihara, who has been a guiding force for our geotechnical earthquake engineering community. Now, the first recipient was Professor Liam Finn in 2004, and he was followed by Professors I.M. Idris, Ricardo Dobry, George Gazidis, Takaji Kokoshu, Jonathan Bray, and then most recently, Akul Tahara. This year's recipient is Misko Cubrinovski. Misko is a professor at the University of Canterbury in Christchurch, New Zealand. He got his bachelor's and master's degrees in Macedonia before moving in 1989 to the University of Tokyo, where he earned his PhD in 1993 working with Professor Ishihara himself. Misko was a researcher. After graduating, he was a researcher for Taisei Corporation for 4 years and Kiso Jiban Consultants for another 8 years. He then moved to the University of Canterbury in 2005, where he has been ever since. Now, Professor Cubrinovski is world-renowned for his profound impacts on engineering practice for evaluating liquefaction around the world, in large part based on the fact he has extensive and balanced use of both theory and case histories throughout his career in looking at these problems. He has published more than 350 papers, including many seminal papers co-authored with Professor Ishihara, evidence of their long-standing and continued collaboration over the years. He's been recognized with numerous awards and honors from the New Zealand Geotechnical Society, as well as elsewhere around the world. And from the US vantage point, he's been recognized with outstanding paper awards from our Earthquake Engineering Research Institute, from the American Society of Civil Engineers, and most notably a Norman Medal in 2016 for the best paper in any of ASE's many technical journals. He was further honored by ASE in 2019 with the prestigious Ralph B. Peck Award, gave a phenomenal lecture at that conference. So the Ishihara Lecture is a fitting recognition of Professor Cubrinovski's many technical and professional contributions to our discipline, and it is my pleasure to now invite Misko to deliver his Ishihara Lecture.
Thank you, Ross, for your kind introduction. I will share my slides. And Ross, please confirm that you can see the slides.
Perfectly.
Okay, thank you. Well, good morning to the delegates in China, and hello to everyone who is following this presentation online. I'm really delighted to deliver the 8th Ishihara Lecture entitled Holistic Evaluation of Liquefaction Problems. I would like to acknowledge the contribution of my co-author, Nikolaos Dritsos, my former PhD student and current postdoctoral fellow. The motivation for this study came from the 2010-2011 Canterbury earthquakes, in which nearly half of the city of Christchurch was affected by severe liquefaction. The eastern suburbs were hit particularly hard, with nearly 60,000 residential properties and buildings being affected by liquefaction. About 20,000 of those were severely damaged and 8,000 were abandoned. The total economic loss due to impacts of liquefaction is estimated at about 15 billion New Zealand dollars, or at 40% of the total economic losses inflicted by these earthquakes. There are numerous images as those shown to the left, illustrating the extreme severity of Christchurch liquefaction. In one of our studies, we investigated in great detail 55 well-documented case history sites. As you can see, the sites are distributed throughout the city, and the red symbols here indicate sites that manifested liquefaction in multiple events. In most of the cases, it was severe or extreme manifestation of liquefaction. Green symbols indicate sites that did not manifest liquefaction in any event, whereas black symbols indicate sites that didn't manifest liquefaction in the first major event in September 2010, but they did manifest liquefaction in the subsequent February 2011 event, which imposed the most severe shaking intensity throughout the city. There were contrasting differences in the performances of these sites, as evidenced here. On the left-hand side, you have an aerial view of a site that didn't experience any evidence of liquefaction, and you can't really see any ground distress due to liquefaction. Whereas on the right-hand side, you can see the image of a site that manifested severe liquefaction with large areas covered on the ground surface with ejected soils due to liquefaction. So with these studies, we tried to understand what are the key factors that were creating this kind of differences in the performances. And it was interesting that we found some important similarities, but also important differences between the two sites that manifested very differently during the earthquakes. On the similarity side, all sites had very shallow water table, and they had also very weak layer close to the surface of low liquefaction resistance, which would be considered a critical layer from manifestation viewpoint. As you can see, that layer is just 2 meters below the ground surface and has low QC1 NCS value of about 80. And this was one of the reasons why the simplified method could not discriminate well between different performances, because in both cases, for sites that didn't manifest and for sites that did manifest liquefaction, the simplified method would predict severe consequences because of this very low resistance layer at shallow depth. We found some important differences in the deposit characteristics between these sites. So sites that manifested severe liquefaction typically were composed of vertically continuous liquefiable soils, meaning all top 10 meters of the deposit were liquefiable soils, as shown by the CPT profile and schematic simplified profile next to it on the left-hand side. On the right-hand side are typical deposit characteristics for the sites that didn't manifest liquefaction, and they are characterized by interbedded deposits composed of non-liquefiable and liquefiable layers. So in our study, we were trying to understand how these differences in deposit characteristics are going to produce different responses of liquefaction when subjected to earthquake shaking. And for that reason, we used the seismic effective stress analysis to investigate those details. I will summarize now briefly some of our key findings from that work. And this is pretty much, this slide is summarizing the key interpretation for vertically continuous deposits, or how liquefaction evolves throughout the depth and time in these deposits. Starting from left, in these deposits, typically triggering first occurs in the critical shallow layer. And this occurs early during the shaking, so the additional shaking is going to cause significant shear strains developing in that layer. Then the underlying soils are developing higher excess pore water pressures and triggering upward flow of water towards the critical layer, which further weakens and fluidizes the critical layer. This also enlarges the zone of liquefaction. So now this thicker zone of liquefied soil is producing strong upward water flow towards the ground surface and inducing liquefaction. Seepage-induced liquefaction occurs in the surface soils. And these three mechanisms then connect to create a mechanism throughout the whole deposit in which the soils from the entire deposits contribute to a very damaging discharge of excess pore water pressures through water flow and soil ejecta. These are all mechanisms that intensify liquefaction manifestation, and this can explain the large severity and extreme manifestation effects of liquefaction that we were seeing in those deposits. From the effective stress analysis, we found that the mechanisms at work for the interbedded deposits are quite different. Typically, this deposit would have loose liquefiable soils at shallow depth, but also in the deeper part of the deposit. So the typical scenario for this deposit was that liquefaction actually first developed at depth, and the softening of the layer at depth was reducing the seismic demand for the deposit and reducing the shear stresses acting on the critical layer, shallow critical layer. This in turn reduced the potential for liquefaction developing in the critical shallow layer. In addition to that, because of the interbedded nature of these deposits, including some plastic soils, the near surface soils were partially saturated. And this further reduced the potential for development of liquefaction in the critical layer. Finally, as shown here, the grid of non-liquefiable layers is preventing any vertical continuity and communication of water through water flow of the liquefied soils. So these three mechanisms eventually resulted in relatively thick crust at the ground surface, and this crust prevented manifestation at the ground surface of liquefaction, even if liquefaction had developed at some depth within the deposit. So these are typical mechanisms that mitigate liquefaction manifestation. Since simplified procedures do not account for this kind of dynamic interactions and system response effects, this was the second reason why they failed to discriminate properly between the vastly different performances that we observed in Christchurch. So here is a brief summary of some of our key findings. First is that dynamic interactions and system response effects significantly influence the liquefaction response of deposits and manifestation at the ground surface. Different interaction mechanisms and system response effects develop in different types of deposits. And finally, the level of the liquefaction response that will develop and the type of mechanisms that will be triggered throughout the deposit really depend on the intensity of the ground motion or excitation. Which brings us to the need to perform holistic evaluation of liquefaction response, which means we are trying to understand how the liquefaction response is going to evolve in the deposit as we are increasing the intensity of shaking. So that is the idea behind this holistic evaluation. So after this brief background, I'm going to provide a summary of the concepts behind the holistic evaluation of liquefaction response. And we'll then move on sharing the results from effective stress analysis of 13 of the 55 sites where we have performed additional analysis within this framework. And then we'll show the result from simplified analysis of the same deposits so that we see what are the key differences and similarities between these two types of analysis. Finally, I'm going to make a very brief comment on the ground motion intensity measures for liquefaction assessment, and will summarize with concluding remarks. So the framework of holistic evaluation of liquefaction problems is applicable to all types of problems, including soil structure interaction, but here we're going to focus on free-field level ground deposits. So when evaluating the liquefaction response of deposits, I would argue that we have to address concurrently three factors in the assessment. The first is the soil response at any given depth, throughout the depth of the deposit. And this is equivalent to what we do in the laboratory when we collect high-quality samples. We test them in the laboratory to identify material characteristics and stress strain characteristics, including liquefaction resistance, and understand how that soil element is going to respond under earthquake loading when considered in isolation. So that is why I refer to this as element response. From the previous discussion and the clear effects of dynamic interactions throughout the deposit, we need to also account for the second factor, which is cross interactions between soils and layers in the deposit and overall deposit response. And finally, the response at any given soil element, as well as the overall response of the deposit, clearly is going to depend on the intensity of the ground shaking. So we have to bring the intensity of the ground motion into the picture and concurrently consider these three factors in the evaluation. So the idea is that we develop this kind of understanding where we can plot on the vertical axis a response measure for the liquefaction effects, and on the horizontal axis is the intensity measure for the intensity of the applied input loading. As response measures, we can use different parameters. It could be thickness of liquefied soil, magnitude of excess pore pressures, horizontal displacement, settlement values, or some damage indices as shown there, LPI, LSN, or EPI. On the horizontal axis, again, we can use different intensity measures. PGA 7.5 will be heavily used. I will explain the reasons why later on. It is not the best intensity measure, and at the end I will address some more appropriate intensity measures for nonlinear dynamic analysis, such as acceleration spectrum intensity and velocity spectrum intensity, and these are measures relevant for assessment of liquefaction response. The idea is that we develop understanding of how a certain response feature is going to evolve as we increase the intensity of shaking. And this may allow us to identify important differences between deposits in their response characteristics, including differences in the mechanisms that lead to those responses. So let's see how now our methods that we use in practice are treating those three key factors. We basically have two approaches. One is using advanced nonlinear dynamic analysis, and the other is using simplified semi-empirical procedures. In the advanced analysis, and the key representative here is the seismic effective stress analysis, all three factors are considered rigorously. For example, to define the characteristics of the soil behavior of a given element, we can recover high-quality samples from the field, test them in the laboratory, and understand and develop good understanding of the stress strain characteristic of that particular material, including liquefaction resistance. Alternatively, we can use empirical triggering relationships to develop liquefaction resistance for a given soil and calibrate our constitutive models, elastic plastic models, to represent the target behavior observed either in the laboratory or derived from empirical relationships. Next, since this is a dynamic analysis in which excess pore pressures and water flow are simulated and dynamic interactions are considered, by and large, seismic effective stress analysis is rigorously simulating most of the interaction mechanisms and system response effects. And finally, the input motion is applied at the base of the deposit as a time history. We can adopt different ground motions, and with that we can examine how the response is going to change when we change the intensity of the ground motion or we change the characteristics of the ground motion. So we have rigorous treatment of all three factors. In the simplified method, liquefaction resistance is typically derived from empirical triggering charts, and I would argue that this is good enough and rigorous enough evaluation of the liquefaction resistance for many of the deposits. We still have some problems there, but generally we're doing a reasonable job there. The second factor is actually not considered. There are no dynamic interactions in this procedure. In essence, for any given layer, we calculate the factor of safety in isolation for that layer without any consideration what is the response in the surrounding layers or the deposit as a whole. And finally, the ground motion is, or the input earthquake load is severely simplified. We are using a couple of parameters, typically peak ground acceleration and earthquake magnitude. The first one is a proxy for the amplitude of shaking, and the second is the proxy for duration or significant number of cycles. And as a combination, they define the intensity of the input load, albeit in a simplified manner. One very important feature is that the load is defined at the ground surface. Because the way the load is defined in the simplified method, and as it differs quite severely from what we do in the advanced analysis, it is impossible to identify identical intensity measures for these two approaches in definition of the ground motion. And I will address that issue later on. So the approach of this study was to select 13 sites from the 55 case history sites from Christchurch and perform seismic effective stress analysis for those sites. We derived numerical models using the CPT data, and for the layers defined in terms of QC1 NCS, then we derived liquefaction resistance curves based on the Boulanger and Idris triggering relationships, and then applied analysis using two ground motions as base excitations. And we increased the intensity of the applied load from very low to very high intensities to understand how the response, liquefaction response, evolved in any of these 13 deposits. And we used this analysis to gain some further insights into the liquefaction response of different types of deposits. The same 13 sites were then analyzed with the simplified method using the Boulanger and Idris procedure. Notice that in both these methods, actually the definition of the liquefaction resistance is identical or equivalent, because in the effective stress analysis, we were using the triggering relationships from the simplified method to define the liquefaction resistance. So for the simplified analysis, also a wide range of ground motion intensity measures were covered. And then eventually we compared the results from the effective stress analysis and simplified analysis to identify key points of similarity and difference. Just a brief reference to how we selected the 13 sites for analysis. Out of the 55 sites, there are 11 sites that we refer to as vertically continuous deposits, and you can see typical simplified profiles for these sites. They're mostly composed of sandy soil. I sub C is 1.5 to 1.7 in these green layers, which are sands. QC1 NCS is mostly 120 to 125, though there are parts of the deposit that are denser, so 150, 160, 170 values for QC1 NCS are also encountered. In the top part, some of those deposits contain sandy silt and silty sand soils up to 2-3 meters depth or 4 to 6 meters depth, as shown with these profiles. So we selected 5 sites which are representing this type of deposits. In addition to that, there are 22 additional sites that have very similar characteristics to what we are seeing here, but they do contain a very thin layer of non-liquefiable soil, which is 30, 40, 50 centimeters thick, as indicated here by this thin gray shaded area. Essentially, these are vertically continuous sites, so we treat them as such, but we added 4 from these 22 sites for our in-depth analysis. And finally, we considered the interbedded deposits. Here are now simplified profiles for the interbedded deposits. There are 22 sites in total out of the 55 with this kind of characteristics. You can see there are a lot of gray layers, so that means there is significant thickness and number of layers that are non-liquefiable. But importantly, in between those non-liquefiable layers, there are many liquefiable layers. And interestingly enough, they all have very low liquefaction and penetration and liquefaction resistance. In this type of deposit, for 9 sites, throughout the depth of the deposit, there is low resistance layer with QC1 NCS of 70 to 80 throughout the depth. Those, all of these layers are sandwiched between non-liquefiable layers. These are similar type of deposits, except that QC1 NCS here is 80 to 100, still quite low. So one key feature of the interbedded deposits is that they have soils of low liquefaction resistance throughout the deposit, including at large depth. So we were investigating, we selected 4 of those interbedded deposits for analysis. So in total, that made it 13. And then we subjected each of these to different levels of intensity of earthquake loading. And we examined the case history database from Boulanger and Idris. This is a CPT database in which there are 253 liquefaction case histories from 19 earthquakes to identify what is the typical range of big ground accelerations for the case histories. So this is the summary for all 19 earthquakes. For example, this black line here indicates the range of PGAs for the Canterbury earthquake. So on the vertical axis, we have the recorded PGAs. So the PGA at Canterbury for the case histories were roughly from 0.18 G to 0.45 G. And on the horizontal axis, we can easily identify the respective PGA 7.5 values. Those are peak ground accelerations for equivalent magnitude 7.5. You can see the distribution of PGA 7.5 values for all case histories. So predominantly, PGA 7.5 was in the range from 0.1 to 0.4 G. And there is a smaller number of case histories that experienced a higher intensity of shaking from 0.4 to 0.65 G. Obviously, these are sites closer to the source. So the conclusion from this was that in the holistic assessment, we have to cover intensities at least up to 0.7 G in terms of PGA 7.5. Which brings us now to the results from the effective stress analysis for 13 case history sites based on using 2 input motions at the base. I will first show a typical and illustrative example how the liquefaction response evolves throughout the deposit. So this is one of the vertically continuous sites. We performed incremental dynamic analysis. So one analysis, say at 0.05 G, then another at 0.08 G, then 0.1 G, and so on, up to maybe 0.9 G. So I'm going to present some of those analyses to share the insights for how the liquefaction response evolves throughout the deposit. There are 5 panels on this plot: RS intensity throughout the depth. This is maximum value of the pore pressure ratio R sub U max throughout the depth. Obviously, a value of 1 indicates liquefaction. This is integrated RU max value throughout depth, maximum shear strain distribution, and maximum displacement, which is approximated by integrating gamma maximum. This is now a result for input acceleration of 0.15 G, at which point the first triggering occurred in the deposit. And we can see the triggering occurs at about 2.5 meters, practically in the critical layer, which has QC1 NCS of 85. If we increase the intensity of shaking, so at 0.3 G, about 2.5 meter thickness of layers liquefied, the softening of the layer due to liquefaction is reducing the demand. You can see a kink in the RS intensity relationship. A further increase in the demand is further reducing the, is further increasing the thickness of the liquefied layer to 6 meters. As you can see, the soil from 2 to 8 meters depth liquefied, and then significant excess pore pressures are also generated below and above that liquefied zone. If we integrate RU in the top 10 meters, we are getting that the total excess pore pressure developed is equivalent to 8 meters out of the 10 liquefying. So clearly, we are getting very significant effects of liquefaction. Importantly, as you can see in these vertically continuous deposits, we are getting very thick zone of liquefied soil. So now we can summarize this type of results by plotting the results in this format. On the vertical axis, we are having now the thickness of the liquefied soil. On the horizontal axis is PGA 7.5, or the intensity of the applied load. This is thickness of liquefied soils that develops pore pressure ratio greater than 0.98 and also developed shear strength greater than 3%, meaning this is thickness of this soil liquefied due to shearing. This is shear-induced liquefaction. So liquefaction triggering occurs at about 0.15 G, and the thickness of the liquefied soil increases. At 0.4 G, we can see 4 meters of the deposit liquefied, and then there is further increase, and we reach the maximum at around 0.7 G, where 7 meters of this deposit liquefied. Importantly, in this case, as we saw previously, all liquefied layers are practically connected, and they create this intensification mechanism because collectively they increase the intensity of liquefaction because of connection of pore pressures and water flow through those layers. The same result here is now plotted with the dashed line, but in addition to the thickness of the liquefied layers, the blue zone is now indicating the thickness of layers surrounding soils that have developed excess pore water pressures higher than the excess pore water pressure at the top of the critical layer. So, for example, in 0.4 G, this implies that there are 7 meters of soils in the deposit that contribute to water flow towards the top of the critical layer. So this is giving some insights about the significance of the seepage-induced effect or water flow effects throughout the deposit, and especially on the critical layer, which is close to the surface. Obviously, using this framework, we can display different types of results. Here is to the right, for example, how the horizontal displacement at the ground surface is increasing with increasing intensity of the ground motion. This is now a summary for the 5 vertically continuous deposits. And we can see some similarities, but also some differences. The red line is showing the result for a relatively loose deposit throughout the depth. We can see early triggering occurs at 0.13 G and relatively rapid increase in the thickness of the liquefied soil. And at 0.4 G, we are reaching the maximum thickness, which is 7.5 meters. As opposed to this response here, where we have denser deposit, actually the triggering occurs in a layer, the critical layer, which has QC1 NCS of about 115. So denser soil in the critical layer, but also throughout the deposit. And that is why we are seeing much slower development of liquefied zone. And eventually the thickness of the soil stops at about 3.5 meters. So the differences that we observe here are due to differences in the densities of the deposit and how different density soils are distributed throughout the deposit. One important similarity is that, as indicated by the symbols here, the symbols are showing us when liquefaction triggered in the shallow critical layer. And this is saying that for 4 of the 5 deposits, liquefaction triggered in the critical layer at shallow depth, at about 2 meters depth. And only for 1 of those, liquefaction triggered at depth, and then there was slight delay of triggering of liquefaction in the critical layer. Let's examine similar type of plot, but for interpelled deposits. Here is again thickness of the liquefied soil against PGA 7.5. Triggering occurred at about 0.17 G at depth. And then it required additional increase in the demand to about 0.25 G to trigger liquefaction in the critical layer. So triggering in depth delayed the triggering in the shallow critical layer due to reduction in demand caused by the liquefaction at depth. Afterwards, we are seeing gradual increase, but limited increase in the thickness of the liquefied soil up to 4 meters, simply because this deposit contains a lot of non-liquefiable soils. So this is the maximum thickness of liquefiable soils, liquefied soils. And then in addition to that, as indicated here, those are actually not connected. So these are individual contributions of separated soils and isolated by non-liquefiable layers. So there is no cumulative effect out of vertically connected soils as was the case for the vertically continuous deposits. In addition to that, we are seeing practically no additional contribution from excess pore water pressures from surrounding soils, which is simply reflecting the fact that the surrounding soils are mostly non-liquefiable. Here I will now, just give me a second to, okay, thank you. I'm going to summarize the results for the 13 deposits. On the left-hand side is something that we have already examined for the vertically continuous deposits. At the center is the vertically continuous deposit with a very thin layer of non-liquefiable soil. And as we can see, they generally have very similar characteristics. One important point that I would like to again emphasize is that in these deposits, typically triggering occurs in the shallow critical layer, as indicated by these symbols that sit on the horizontal axis. So 4 out of 5 here liquefaction triggered in the critical layer, and for 3 out of 4 deposits here, liquefaction triggered in the critical layer. The second important thing is that triggering occurred at relatively low intensity. As you can see, somewhere between 0.1 and 0.2 G for most of the sites, except for this one here, and the reason for that is the higher density of the critical layer. The response that we observed for the interbedded deposits is a bit different. Triggering occurs at low values of PGA, 0.12 to 0.16, but at depth. This triggering at depth is reducing the demand throughout the deposit and delays the triggering in the critical layer. Shallow critical layer. So triggering in the shallow critical layer occurs somewhere from 0.2 to 0.3 G. As I mentioned previously, in the shallow part, these deposits are sometimes partially saturated. If we account for partial saturation, this delayed triggering may be pushed further to the right because of the increase of liquefaction resistance due to partial saturation. Another important difference is that the maximum cumulative thickness of liquefied soils is relatively small for these deposits, and also those are contributions for isolated layers separated by non-liquefiable soils. So in summary, we can characterize the typical evolution of the liquefaction response for vertically continuous deposits from effective stress analysis in this way. Triggering typically occurs in the shallow critical layer at low intensity of shaking. And then the response or thickness of the liquefied soil evolves either more rapidly for loose deposits or more gradually for denser deposits, and eventually reaches a reasonably high thickness, especially for looser deposits. These are thick zones, connected vertical zones of liquefied soils, and those create really conditions for severe or extreme manifestation at the ground surface. The interbedded deposits show different response. Triggering also occurs at similar intensity levels, but at depth. And this delays the triggering in the shallow critical layer. Eventually, we are getting maybe cumulative thickness of liquefied soils of 2, 3, 4 meters, which is much smaller than in the case of vertically continuous deposits. And as emphasized previously, those are contributions from layers that are isolated and separated by non-liquefiable soils. So there are some clear and important differences in the evolution of the liquefaction response between these two different types of deposits. So let's now compare these results with what we observed from simplified analysis. I will do the same animation as before for the same profile to illustrate how liquefaction response evolves in the simplified analysis. So this is now analysis for PGA 7.5 of 0.17 G. Triggering occurs pretty much in the same layer at similar intensity level. There is also triggering at slightly deeper, a larger depth at 5 meters, which is reasonable because we have another weaker layer with QC1 and NCS of 105 there. If we increase the intensity to 0.3 G, we are getting larger thickness of liquefied soils. And if we further increase the intensity at 0.4 G, most of the deposit liquefies. So generally, we are seeing very similar thing. But if we want to compare results from effective stress analysis and results from simplified analysis, we really need to compare them for identical intensity of the earthquake load applied in both analyses. Unfortunately, because the way the earthquake loading is specified in the simplified method, it is impossible to identify identical intensity for these two analyses. At best, we can get close to similar intensities. And a parameter that is providing that is PGA 7.5, and that is why we have used it so far in all these plots. PGA 7.5 is peak ground acceleration for equivalent magnitude 7.5, and we estimated it for each of these analyses by converting the irregular time history that we applied at the base of the input motion to uniform amplitude series. And in that process, we adopted 15 cycles for the magnitude 7.5 earthquake, and the exponent in the magnitude scaling relationship was 0.34. Obviously, PGA 7.5 in the simplified analysis can be easily calculated by using the PGA value, the earthquake magnitude, and the magnitude scaling relationship. Even though they're both called PGA 7.5, the way we calculate and define them is obviously very different. So we're kind of comparing apples and oranges to some level. Fortunately enough, what we found was that the triggering PGA 7.5 that caused triggering in the simplified analysis was very similar to the PGA 7.5 triggering that caused triggering in the effective stress analysis. As you can see, for 11 of the 13 sites, the triggering values in simplified and effective stress analysis are within 15% difference. There are two sites that differ more. One is denser deposit, and the other is very soft, non-liquefiable layer in one of the interbedded deposits that heavily affects the response in the effective stress analysis, and this effect is not accounted for in the simplified analysis. But generally, we are getting the triggering is at the same level, which really facilitates now the comparisons that I am going to show next. So this is now comparison of the observed responses in terms of thickness of liquefied soils in relation to the intensity of the applied load. The black line is showing the response of the effective stress analysis, and the blue line is showing the response from the simplified analysis. We can see much steeper rise of the thickness of the liquefied soil in the simplified method as compared to the effective stress analysis. For example, at 0.22 G, 5 meters of soil are going to liquefy according to the simplified method, whereas only 1.5 meters of soil are going to liquefy according to the effective stress analysis. In order to liquefy 5 meters of soil in the effective stress analysis, we really need to double the intensity from 0.22 to 0.43 or something like that. So much slower buildup of thickness of liquefied soil in the effective stress analysis. And we attribute this to the reduction in the demand due to softening of the soils and liquefaction occurring somewhere in the deposit. And this response was observed for all types of deposits. This is now envelope result for 3 deposits, vertically continuous deposits. So the simplified method is this blue shaded area, and the gray area is the result from the effective stress analysis. The horizontal scale is slightly modified here. As you can see, this is now PGA 7.5 minus PGA triggering, which means triggering is at 0. So everything has been brought to the same point of triggering. And what we are observing is how the response evolves post-triggering and what are the key differences. So clearly there is significant delay in the evolution of the response of the effective stress analysis as compared to the simplified method. This is an equivalent plot for two denser vertically continuous deposits. And again, to achieve the same response in the effective stress analysis, we really have to increase significantly the intensity of the input motion. There is another important difference that I would like to highlight here. In the simplified analysis, for example, as you can see, both looser and denser deposits eventually achieve very high thickness of liquefied soil of about 7 or so. In the effective stress analysis, the denser deposit, even when you subject them to high intensity motions, because of the interactions that develop in the deposit, will show smaller thickness of liquefied soils. So in other words, by introducing these interaction effects and system response effects, we are going to bring the capacity to better discriminate between different performances. As you can see at the end, the effective stress analysis is predicting only half of the thickness of the liquefied soils that the simplified method is predicting for the same deposits. I will bring now a little bit more detail. 4 out of the 13 deposits has this kind of configuration in the soil profile, where you're having a critical layer of low liquefaction resistance, QC1 NCS 79 in this case. And deeper in the deposit, there is another layer with very similar QC1 NCS value, TL indicated here. So let's compare how the responses in these 2 layers develop in effective stress analysis and simplified analysis. So the blue line here show how the maximum shear strain evolves in this layer, TL, as we increase the intensity of loading, PGA 7.5. So clearly triggering occurs at about 0.1 G, and as we increase the intensity of shaking, larger maximum shear strain develops in that layer. The response in the critical layer, shallow critical layer, is shown by the red line. Because liquefaction first triggers in the deeper layer of equal penetration resistance, there is reduction in the demand throughout the deposit, and we need to increase substantially to 0.22 G the intensity of the input motion to trigger liquefaction in the shallow critical layer. And then you can see how gamma maximum evolves as we increase the intensity of shaking in the effective stress analysis. The respective results from the simplified method are shown with the dashed lines, where you're seeing, again, first triggering in the deeper layer, because simplified method also through CSR is predicting the deeper layer should liquefy first. And then you're having the steep rise in the maximum shear strains for both layers. So at 0.2 G or something like that, both layers reach the maximum value of about 25%. The solid lines here were obtained when we used ground motion 1 from the Canterbury earthquakes, and we repeat the analysis using another ground motion, so GM2, and you can see similar response. Actually, in this case, there was even further delay in the triggering of shallow liquefaction in the shallow critical layer, clearly showing some significant effects of the interactions throughout the deposit on the response in the shallow part of the deposit. Obviously, the simplified method response is the same here. So what we then did for all 13 deposits, we summarized the results for the maximum shear strain developing throughout the deposit for different QC1 NCS values. For example, the red line and red shaded area shows all layers in the 13 deposits, how they develop the maximum shear strain as we increase the PGA 7.5, irrespective where they are located. Some are shallow, some are deeper. And this shows that all layers of this low resistance are sharply going to develop very high maximum shear strengths. You can see now the orange line is for QC1 NCS 80 to 100. The green is for 100 to 125, and then we go towards denser deposits. Especially for these 3, we are seeing very sharp rise of maximum shear strains. And effectively, for all soils with QC1 NCS less than 125, maximum shear strains will be reached at 0.25 G. So everything will be not only triggered, but everything will develop the maximum strain response. And this is reflecting this flat part in the triggering relationship. Once we go beyond this kink, there is significant increase in the liquefaction resistance, and that is why we're getting larger separation of these 2 relationship here for denser deposits. There is no any effect of interactions in this response. And this is quite different from what we observed from the effective stress analysis. Here is the equivalent plot for the 13 deposits from effective stress analysis for the same grouping of QC1 NCS. We are seeing significant delay in the development of large shear strains due to the interaction effects. And it is very much pronounced for, especially for this response for QC1 NCS from 100 to 122, because at 0.25 G, for example, in the effective stress analysis, those soils have not yet triggered. In order to develop maximum shear strains, you really have to go to 0.5, 0.6 G at much higher intensity levels. So this is suggesting that the dynamic interaction effects are extremely large for the evolution of the liquefaction response and shear strain throughout the deposit. My conclusion is that the simplified method is doing a reasonably good job for triggering in the loosest layers. However, once we have triggering, the effects of the triggering of liquefaction is not reflecting the effects of the reduction in demand and consequent delay in triggering in the other layers. And that is the key reason for the large difference that we are seeing here. At the very end, I would like to make just a brief comment on the ground motion intensity measures for liquefaction assessment, which is related to what I was presenting so far. I'm showing again here the maximum shear strain versus PGA 7.5 obtained from effective stress analysis. So the solid lines obviously are for different QC1 NCS values when we used ground motion 1 for the analysis, and the dashed lines are for ground motion 2. So clearly we are getting different responses or non-unique response, meaning the ground motion characteristics are affecting this response. And the reason for that is because we are using PGA 7.5 as an intensity measure, which is not the optimal measure. We use PGA 7.5 because that is the measure that we can use to compare effective stress analysis and simplified analysis. Probably is the most practical, if not the best, certainly the most practical measure to use for those kind of comparisons. In order to understand better what intensity measures are best to use in liquefaction assessment, we performed 180 effective stress analysis to all these deposits. So each deposit was subjected to this number of analyses, and we were using 108 different ground motions that Bradley used in his study earlier. Now, each motion was scaled modestly from 0.6 to 1.6, and these are motions from 19 different earthquakes with this range of magnitudes. This presents results from one of the sites. Each symbol obviously here represents one result from effective stress analysis, and the median response is shown how it increases with the intensity of the applied motion. And clearly there is large scatter here because we are using PGA 7.5. If the same data is replotted in terms of acceleration spectrum intensity, there we are seeing reasonably well-defined correlation between the liquefaction response and the acceleration spectrum intensity, despite using over 100 different ground motions. So our conclusion was that actually, if you identify appropriate measure, we are getting very well good correlation between the liquefaction response measure and the intensity measure. The general conclusion is that acceleration spectrum intensity works reasonably well for response measures, including excess pore water pressure and shear strains, whereas the velocity spectrum intensity, as shown here to the right, where maximum displacement is plotted against VSI, is really providing good correlations when the shear strain is part of the response. So by using appropriate ground motion intensity measures, we are significantly reducing the scatter in the liquefaction response in relation to the intensity of the input motion. And finally, these are results for 12 sites. So please don't look at all 12. Let's focus on only one here. The second from the left at the top is for one of the sites. All plots are showing the same thing. So again, we have 180 analysis, and the green line is showing the median response. GM1, that is ground motion 1 that we used in the analysis, was recorded at in the Canterbury earthquakes. And you can see that it is very close for small intensity. It is very close to the median response because we are applying small scaling factors in that case. But here, the scaling factor is significant. It's 3, 4, 5. And you can see that the response produced by that unreasonably scaled ground motion is far exceeding the overall trend and even the outliers, and certainly is far away from the median response. So it's important to use modest scaling when performing a liquefaction assessment. And we can use different types of ground motion characteristics. The second important conclusion out of this is that the difference that we were seeing before between effective stress analysis and simplified method would be even more pronounced if we use the average, the median response, instead of the response that we showed, which was related to the ground motion 1. And this brings me to the concluding remarks. So 3 factors, those are the element response, system response, or interactions, and ground motion intensity should be concurrently considered in the liquefaction evaluation within the holistic evaluation framework. Effective stress analysis shows significant effects of dynamic interactions on the evolution of liquefaction response and consequent manifestation. The type of interactions, response mechanisms, and overall deposit response depend on the characteristics of the deposit, not only on the type of the deposit, but how densities and layering is distributed throughout the deposit. For vertically continuous deposits, which are composed entirely of liquefiable soils, triggering of liquefaction typically occurred in the shallow critical layer. And this sets the first and foremost condition for severe liquefaction manifestation. When this occurs, I would argue that severe manifestation is guaranteed in most of the cases when you don't have obviously thick crust of non-liquefied soil. Interbedded deposits in Christchurch have low resistance layers at large depth, and triggering typically occurs first at depth. This delays or may even prevent triggering of liquefaction in shallow soils, and hence is a mitigating factor for shallow liquefaction. These are now some conclusions for the simplified procedure. Simplified procedure ignores dynamic interactions and system response effects and shows very rapid evolution of the liquefaction response from triggering to the maximum response. And this reduces the capacity of the procedure to discriminate the responses of deposits, especially in the range of QC1 NCS below 125. As all these soils reach the maximum response within a very narrow range of demand, in our analysis from 0.15 G to 0.23 G. Hence, the conclusion is that effects of interactions and system response should be incorporated in the simplified procedure, albeit in an approximate manner consistent with the overall approach of this method. And a couple of conclusions on the ground motion characteristics. It is on the intensity measures for the ground motion. It is impossible to identify an identical intensity of the input earthquake load for the simplified and effective method and effective stress analysis. But PGA 75 is probably the best, if not the best, I would argue, certainly the most practical proxy for this purpose. And finally, ground motion intensity measures such as acceleration spectrum intensity and velocity spectrum intensity provide very strong correlation between the liquefaction response and ground motion intensity, despite the variety of ground motion characteristics in the adopted input motions. These are some of the references that I have mentioned in the presentation, and I would like to acknowledge the great collaboration and contributions from many of my colleagues in New Zealand and overseas, and US especially. And in the end, special thanks to Professor Ishihara for the 15 wonderful years of working closely together. We had hundreds of insightful discussions on various topics continuously. There was a period of 3 to 4 years when I was in Taisei Corporation. We would arrange to meet at a station where our trains were crossing pathways, would go to a coffee shop and start discussing issues over coffee. Quite often we'll go for hours and have lunch at the same place. And those discussions are some of the most treasured memories in my whole career. Thank you very much for that great experience. And thank you all for your attention.
Thank you, Misko. That was, as expected, a masterfully presented lecture. It's insightful, practical, fundamental, as always. Real pleasure listening to that. I want to check whether my co-moderator, Lan-Min, were you able to make it back for the session? Let's see if Lan-Min made it back. Maybe not.
Should we not give Misko the appropriate?
Yes, Professor Ross.
Yes.
Yeah, I come back.
I thought you might like
please.
to add.
Do you have do you have the question? Can you hear me?
Yeah, we're almost to, I think, the end of the session, so it might be hard to do a question this time. I think, Misko, I would add that just on behalf of the TC203, everyone was extremely happy to see you be the recipient of the Ishihara Lecture. Your longstanding relationship with Professor Ishihara is very well known to everybody. And we appreciate all the contributions. Your list of all the different collaborators speaks to how well the community has really traveled to work with you and all the things you've learned from a terrible sequence of earthquakes in 2010, 2011. And maybe if everyone can, I'm not quite sure, virtually or together, if we could give Misko a round of applause.
Thank you.
Hopefully we see some hands.
Thank you, Ross.
Thank you, Misko. Lan-Min, I'll leave it to you for any business to close the session.
On behalf of the chair of the technical committee on earthquake geotechnical engineering and associated problems, Professor Rose and me will present a certificate of Eighth Ishihara Lecture to Professor Misko. Please, we three have a group picture now.
Thank you.
Thank you for your excellent lecture.
Thank you.
Okay. Thank you, Professor Ross. You take everything very well. Thank you. So Ishihara Lecture is closed.